Alright, welcome back, Seventh Hour. This is not the most ideal way of meeting, but this is the best option I got for you right now. Today we're going to talk about ecology again, the final section for our ecology unit, cycling of matter. This will be the third and final section for the test, so pay close attention. Alright. So our objectives are to describe how nutrients move through the biotic and abiotic parts of an ecosystem, and recall that biotic are living and abiotic are non-living. We're also going to explain the importance of nutrients. So nutrients are things that you need in the environment, so how important they are and where do we get them from. We're also going to compare the biogeochemical cycles of nutrients. So if you break that word down, we know that bio means life, geo is talking about like earth, and we know that chemicals usually mean chemicals. So life, earth, chemicals. So chemicals found on earth that grant life to us. So we're going to talk about those and how important they are. Main idea, essential nutrients are cycled through the biogeochemical process. So the main ones that we need are constantly being replenished over and over and over again. Cycles in the biosphere. Flow of energy in and out of the biosphere, only set amount of matter. And we know that is true due to the law of conservation of mass or matter. This says that matter cannot be created nor destroyed. It is just right there. So whatever we see, that is the amount. Okay? Matter is defined as anything that takes up space and has mass. Do you take up space? Do you have mass? Then that's right. You matter. Yep, that's right. You matter. The law of conservation of mass, once again, says that nothing can be created nor destroyed. So therefore, everything must come back around one way or another. And when you think about it, you are just a bunch of recycled matter that has been processed through millions of years, billions of years. Some of the atoms that make up you could be the same atoms that make up a dinosaur in the past, or a plant, or something else. It just all comes back around. All right? So what are the nutrients that we actually use in our everyday life? Some of the most important ones. Many of them you could say are vitamins and stuff like that. But even vitamins and other things are made up of atoms. Okay? So atoms, the most important atoms are carbon, nitrogen, phosphorus, oxygen, and hydrogen. When you think about it, these 5 nutrients or elements are the most important to your overall body. When we say, hey, humans, we are carbon-based life forms, it's meaning that the majority of your body is made up of carbon. And not just humans, but squirrels, rabbits, you name it. Just about every organism has carbon as a foundation. And if we go back and remember why carbon is so important, it's because it can make 4 bonds, because it has 4 valence electrons. So it can bond with just about anything. So it's very diverse. It's like the MacGyver of the atoms out there. And you think about nitrogen, how prominent it is in our atmosphere. Phosphorus and nitrogen both found in DNA. Oxygen, also very, very important. And hydrogen, it's like that accessory element that just bonds with everything to fill in. So very, very important. And you can see in the lower right picture, that is a molecular structure of a carbon chain. You'll learn more about this when you get to chemistry, the ball and stick model of using different colors and shapes to represent different atoms and how they're arranged. So nutrients, they're cycled once again through the biogeochemical cycle. By definition, is a process by which matter is cycled through the biosphere. Now, I really like the picture here. As you draw your attention to that, you can see that the sun, as we know, is the ultimate source of energy, granting plants that 1% energy, which then plants, of course, getting eaten by primary consumers, passing on 10% of their energy as we go down. But as you look at it, the sun supplies that energy, the plants do photosynthesis, the plants die. They decay into the ground, which creates soil, which is very important. When you create soil, you create new plant matter, which can be uptaken by heterotrophs like us, that sheep down there. They eat grass, they leave waste, and stuff like that. And then it goes back to the plants, waste does. And plants need fertilizer. They grow again. Once again, we can take those plants and we can process them through factories to get energy over time. And that releases emissions. And that's a big old CO2 cycle. So even you partake in that with respiration and all these different things. So everything is constantly being recycled over and over again. The water cycle is very important to us. You can go longer without food than you can water. Experts say that you need at least a half a cup of water a day, and that's once again depending on the humidity, temperature, your prior state, stuff like that. So, but you need a little bit of water each and every day. And some of you are like, I didn't drink any water yesterday. How am I still alive? Keep in mind, a lot of the food that you eat grants you water, has water in it. If you eat pasta, think about how those noodles were, rock solid, but then you boiled them in water and made them, softer. That contains a lot of water that you just consumed. Didn't drink it, but you ate it, which your body can then break down and get. So keep in mind, a lot of the things that you're eating every day contain water. It's one of the most essential elements or nutrients for life. Okay, pollution, as some of you did in your ecological studies, is a serious impact. If you have polluted water, it's huge because it can cause you to become sick. People can't drink it. You hear about in the news sometimes, they're under a boil effect. It's because they had a water break and they're concerned that there might be bacteria that could cause people to get sick. So they're very, very cautious about what's going on with our water. But keep in mind, every time you turn on that faucet, 9 times out of 10, it's going to come out clean, clear water. Even if it's a little murky or dirty, it's not like the people in the upper right there. That's clean, fresh drinking water to them. And if you look in the background, I'm sure those camels drank out of it. I'm sure there was other animals that traced around in it, and they might have poop on their feet. But that's clean drinking water to them. Most of us wouldn't even, think twice about looking at that. But that's clean to them. And they have to go several miles for that sometimes. So the water we have here in the United States, even though you may not like it, think it's dirty, it doesn't taste right, at least it tastes better than that. Right? Many countries do not have clean, clear water like we do. But there are serious impacts on life, just pollution alone, antifreeze, oil, herbicides, pesticides that can get in the water, which cause problems for us as humans, not just us, but wildlife, like salamanders, fish, and things like that. Going back to biological magnification, building those toxins up. You eat the fish, then now you have toxins. All right. The U.S. government has even predicted that future wars will not be fought over oil, will not be fought over land. It'll be fought over one very important thing, and that is water. Water is a very, very important thing to us. Right now, we take it for granted, but when you think about it, other countries, they say when you go to Mexico, don't drink the water. The reason why is it has bacteria down there that we're not accustomed to. It can make us very sick. My brother worked on the road, worked in Oklahoma. Everybody on the road crew got sick for about 2 weeks, and they couldn't figure out why. Then they realized it was the water. They were all drinking it. They had bacteria in the water they weren't used to. The water purification system down there was not good. So think about that, how big of an impact just even the United States moving across state lines can have on you. All right. We do even have tensions between United States and Mexico over the Colorado River. When we dammed it up, all the water started flowing down and stopped. Mexico's like, hey, there's no water down here. And we're like, yeah, we understand that. And they're like, you need to let some more out. And they're like, get your own mountains. So technically we own the mountains where the water comes from. We can control the source. So Mexico's not very happy with us about that. It hasn't been for years. So water. Very important to us. But the water cycle, you think about how water moves around the environment. This is a big thing. You've got evaporation, you set a glass of water out in maybe the wintertime, like when it's, you got your furnace running. And, you come back 2 or 3 days later, you forgot about that cup of water, and it's gone. It's like, who drank my water? Nobody did. The dry air that your furnace kicks on and moves around causes all that water to evaporate. So it's changing from liquid water to water vapor, and it goes out into the atmosphere or the air around you. Even now, around you, there is water. Right? You especially feel this during the summertime with humidity. That's why Missouri's summers are so awful, is because the water molecules around you are heating up. You step outside and it feels like stepping out into an oven. But if you go to Arizona, the humidity is much less. When it's 100 degrees out there, it doesn't feel that hot compared to Missouri because there's less water. Condensation, water vapor changing to liquid water, right? And this is a very common thing. It's been a hot summer day, which some of you might have already done this. Went outside, mowed the lawn, worked up a good sweat, and you come inside, and it's just so hot. You go to the refrigerator, you open it up, you stand there for a while because you're like, oh, it's so nice, right? And your mom screams at you, get out of the refrigerator. So you grab you a can of Mountain Dew, and you drink. You go to the living room, prop your feet up on the coffee table, grandma's antique coffee table, and then you open up your can of Mountain Dew, take a big old swig, and you sit on the coffee table, and all of a sudden mom comes screaming in there again, get a coaster underneath that, right? Why is she so concerned about it? Because condensation. Your Mountain Dew can will start to condensate because it's cool. The water molecules and air will stick to it. They'll run down the side, and then they'll create those nice little rings on the coffee table there. And if you can strategically place them, you can make the Olympic rings. Just so you know, moms don't find that funny. I tried it. It doesn't work. So just put a coaster underneath there before she beats you with a wooden spoon. All right? Transpiration, water vapor leaving the leaves of plants. So we've talked about this during photosynthesis. Once again, when plants open up their stomatas, they're trying to exchange that oxygen out for CO2. But in doing so, they can actually lose water out those stomatas. So this is once again going back to the C3 and CAM plants adapting to those hot, dry days. So transpiration is just water vapor leaving the stomatas of plants, and you can see that in the picture in the lower right. All right. This is just kind of a nice little picture showing you the water cycle, how water can actually move through it. And many of these things are quite common. Dew, when you're out there in the summer, and so really late night, and you're playing baseball or something, it's one of those late games like 9 o'clock, and all of a sudden a heavy dew comes in, your helmet's wet, your bat's wet, the dusty soil settles all of a sudden. So that's dew. Sometimes it's in the morning, and you feel that. You go out there to get the newspaper and you shuffle through the grass and your socks are completely soaked. So the dew, it's just moving water, kind of like condensation. Mist, that's when rain, of course, is not really raining, but it's not really like not raining. It's like the worst possible scenario ever when driving. When you get your license, you'll understand. There's no setting known to mankind for the mist. Like you turn them on and your windshield wiper goes gets rid of it. You're like, all right. 30 seconds later, it's all gone. And it's like really light, and all of a sudden you get your windshield wipers like, right? And you're like, wow, okay. So you turn them off, and then it's like you can't see again, and then you start the whole process over again. So mist, not much fun. Fog is another one where it's just basically water molecules sticking to dust particles, which create clouds, and that's what you see in the sky or clouds. It's just water vapor and dust. Rain, of course, we have all seen that. Canceling track meets and baseball games alike. Hail is when you have a lot of updraft, which causes the rain to go back up higher in the atmosphere, and then it's cooler up there, and it freezes, and then the water molecules stick to each other, creating these bigger balls of ice, and eventually the wind cannot keep the ice or rain up any longer, and then they fall down. And as they fall down, they can cause serious amounts of damage, and you do not want to be out in a hailstorm. They can get as large as, some cases, like a softball size, which, if you can imagine a softball size chunk of ice flying down at you from the sky, yeah, that would kill you. Snow, of course, our lovely snow, and why we have to go so many more days, snow days, so that's nice. You got precipitation, rain, sleet, snow, or hail, as we talked about. You have runoff, percolation, and groundwater as well. Runoff is when the surface water from precipitation flow to tributary streams, rivers, lakes, and oceans. And this is the type of water that is on the surface. So if you're driving down the street and you see a bunch of water moving down there on a rainy day, that's runoff. You can literally see the water on the surface. Okay, maybe it's in your yard. You can see it running off your yard, trickling out, whatever it is. It's runoff. If, however, it's moving beneath the soil, so after it rains and you've got maybe a yard with a hill on it, you go outside, you can hear the little trickling of the water through the soil. That's percolation. It's moving underground subsurface. And the soil, yes, will allow water to move typically, unless it's straight up clay. Groundwater, aquifers are water stored underground. So deep down in the ground, they can have certain rock layers or beds, whatever, and it can actually pool up water, and these create aquifers. And we'll talk more about those here in a second. But this is kind of a picture. If you had, let's see if I can get my drawing tool to work here. The water here from the rain cloud, and it moves across the surface down to the ocean or wherever, the lake. That would be runoff. When it moves beneath the soil, and then all of a sudden it goes through the soil down to the lake or ocean, that would be your percolation. When it gets trapped deep down in there because of the rock layer below, then it creates this aquifer. And sometimes these aquifers don't run out into lakes or oceans. That there could be a big old pile of stuff right here that's blocking it. And that could be just a huge reservoir, like an underground lake of water. So, which is pretty cool. All right. And again, that's just, it could be anything. All right. So that's your percolation, runoff, and aquifers. So the water cycle, once again, showing you kind of the amounts with some numbers, some units. The units are not really relative to anything, but you can see like the ocean down there, it's got a whole bunch of stuff, water. And that's, when you think about 2/3 of our planet is covered in water. But you got some evaporation going on. You got precipitation, which is rain. And you got to realize there's a lot of rain over top the ocean, right? But some of it will move across and then rain on land, which gives us the water that we see, all right? But you got the runoff, you can see down there in 36, evaporation, once again, coming from rivers, streams, lakes, all that. But then you got sedimentary rocks near the surface that also hold a lot of water. So once again, deep within the soil, we can have water. Okay. Now, this is an interesting case. It's called the Olagala Aquifer. And if you've never heard of this, it's quite interesting because there's a massive aquifer, basically like a giant underground lake, kind of like the size of the Great Lakes, but maybe even bigger. It's all within, as you can see, these states over here, from South Dakota all the way down to Texas. The big spot is, of course, in Nebraska. It's the deepest and most concentrated. But this has been known for quite some time. It has huge impacts on farming. When you think about it, how much rain they get out in western Kansas, Nebraska, South Dakota, Oklahoma, it's not a lot. They don't get nearly as much rain as we do here in northern Missouri. So how do they yet, grow all these crops? When you think of Nebraska, you think of corn. So how is it even possible that they can grow that much stuff with less water? And it's because many farmers are tapping into the Olagala Aquifer. As they do so, they're pumping out that water, which is nice, spring-fed water basically, onto their crops. And that's how they do it. They have these crop circles, which are these irrigation systems that go around and around and around circles and spray them. And that's how they get by. But there is a huge impact on this. And the problem is that the aquifers are starting to become depleted over time. And as they get depleted, they'll eventually run out. And if they run out of water, they can't grow crops in Nebraska. They can't grow crops in western Kansas, which are notorious for farming. Big impacts on things like corn and wheat and soybeans and molasses and stuff like that. You're like, do we really need all that much corn and stuff? Think about all your Doritos, your tacos, all sorts of things have corn in them. You don't even realize high fructose corn syrup, which is in all of your sodas. So your price of a soda might be, say, $2 right now. Would you pay $5 for one, a 20 ounce? Would you pay $10? It could get that drastic if we don't have the crops there to supplement those prices. So pretty big impacts overall. So this is something that, yes, you should be concerned of. How does it refill the aquifer, you might ask? By rainfall, natural rainfall. But once again, do they get a lot of rainfall? No. And they are actually taking more water out than what is going in. There are locations, as you can see, like in this old-time photo here, sinkholes that start to occur. There was one photo that my college professor showed us, and it was really interesting. It was a place out in Kansas or Nebraska, and they had marked on the telephone pole the elevation, just so you could see how much it changed. And at the very top is when they had the original town elevation. And then they posted signs right and left just so you could see the years of how much it changed, the elevation. It had dropped the entire length of a telephone pole, which are pretty big. Think about that. The elevation of one single area dropping the entire length of a telephone pole in over like 20, 30 years. That's huge. just because you took water out of the subsurface. That's big. Now you might be thinking, how does it not like collapse into this, void of underground lake, right? Well, keep in mind that aquifers, once again, are not just like solid, water. Sometimes they have sediments in there and they're pockets of water. And keep in mind, there's big rock structures underneath that are still holding up the mainland. Okay, so it's not just like water, just you can go dive down in there. Okay, so it's not just a perfect big swimming pool. All right, so you can see in that picture on the lower right, showing you that there are sediments and stuff in there creating this aquifer. All right, rocks mainly. So the question is, why and how did we get this huge, massive aquifer out there in the Midwest, basically? How's that possible? Where did it all come from? What do you think? Well, look right next to it. There's Colorado and Wyoming, and you go on down, there's even more states with the Rocky Mountains. They believe after the Ice Age, the Rocky Mountains, of course, had a bunch of snow and ice on them, that all that snow and ice had to go somewhere from those glaciers, and it washed down the Colorado Rockies, bringing with it large amounts of sediment and water. And as it did so, it filled up that area, and then all of a sudden, it just completely covered it all up and made a hard surface, and there's a whole bunch of water from that last ice age that was deposited down there. Now, if you've ever been to Colorado, as you get out towards Kansas, the western edge, and then all of a sudden it's like flat, 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 and then all of a sudden it goes up. The elevation changes quite a bit. You're asking, why did the elevation change? That was the delta from the runoff from the mountains, which means a bunch of soil and sediment all washed out and then kind of stopped. And that was what you were seeing, the delta. You could actually drive up the delta, right, if you've ever gone out that way. So very interesting. Olga Aquifer, big impact on farming, something that you should look into in the future. Okay? The carbon-oxygen cycle. We, of course, have photosynthesis, which, once again, is your process of taking in CO2, putting out oxygen. You've got respiration, the process of taking in oxygen and releasing CO2. That's what you do, and plants as well, keep in mind. Combustion, the burning of fossil fuels for energy. Release of carbon dioxide. So every time you burn gasoline in your car, you're releasing those fossil fuels back as carbon dioxide, which is, once again, a greenhouse gas. Decomposition, the breakdown of dead material, leads to the formation of fossil fuels and stores CO2. So every time a tree dies and it gets covered up with dirt and doesn't get rotten away or burnt or anything like that, you're taking the carbon out of the atmosphere and putting it back into the soil, which once again makes a lot of organic material later on. This, given enough time, could turn into coal or oil. Diffusion moves CO2 in and out of the water. Most people don't realize, but the ocean acts as a huge sinkhole for carbon dioxide in the atmosphere. So carbon dioxide is out there and it will slowly diffuse into the ocean, making carbonic acid. The same thing that's found in your soft drinks, those bubbles that you love so much. That is the same process of carbonating the ocean. Okay. In doing so, carbonic acid is an acid which lowers the pH. And we know that if you lower the pH of a solution too much, then it can cause problems for the ecosystem, killing off wildlife. Specifically, they have linked this to the degrade of the coral reefs. Coral reefs are starting to die out. They couldn't figure out why until they started testing the pH. It's changed ever so slightly, causing many of the organisms there, the coral, to die off. So our impacts are everywhere. Even though it's, getting a little warmer, some of these subtle changes are so big for some organisms, they can't withstand them, and they're disappearing. We do know photosynthesis just by a run through, once again, taking sunlight, carbon dioxide, water, putting out oxygen and good old glucose. Photosynthesis, yet again, you can see, happens in the chloroplast there, specifically in the thylakoid membranes. As you remember, the light-dependent reactions, and then on the lower left you have the light-independent reactions, which is known as the Calvin cycle, which put out sugars, which can be used as structural components or energy that can be broken down into ATP. This is the cellular respiration process. Once again, this is what you and plants also do. Okay, but you're once again taking in sugars, once again doing glycolysis out there in the cytoplasm. Then you're going to move the pyruvate into the mitochondria to do the Krebs cycle and the electron transport phosphorylation. And that's how you get your good old 36 ATP from one molecule of glucose. And the mitochondria is the powerhouse of the cell. Good job. Combustion, once again, this is how, once again, we take coal, and if you've never been to the Thomas Hill factory or understand how it works, you really need to check it out. They take coal, they powderize it, they throw it into a furnace to burn it up, and then therefore they create a steam turbine engine, which causes the fan to move, which causes a rotor to move, once again creating electricity with the electromagnets. And that's how it's powering the lights, powering the screen, powering this video, all this stuff in our area. So, very important process to live out our daily lives. Diffusion, once again, just to touch base on this, you got the carbon dioxide going into the atmosphere, once again from fossil fuels or from what we do, or whatever it is, but it can diffuse into the oceans, making this more acidic. All right, and that's not necessarily good because that can kill off, once again, the coral reefs. So lots of different things going on here. But you can also see that we have coal, oil, and gas, which once again can be burned. That can, through factories, be released. That was stuck down in there, taken out of the atmosphere a long time ago. Limestone and dolomite, which is basically like marine life, the shells of like clams and stuff like that. They have to go somewhere. They build up in layers and layers and layers. I'm going to show you a really cool photo here in a minute. But trees, they can die and go into the coal and oil and gas, or they could be, releasing carbon dioxide themselves, just like we do. But a number of things. So you can see this whole system is connected. And when the whole system is connected, I mean, you can have big impacts if you mess it up. So we got to be careful what we do. This is the carbon-oxygen cycle, just showing you some different numbers. Yet again, you can see deep down the ocean, we got lots of water, or carbon cycle, sorry. But you can see the carbon at the shallow is there, but deeper down, you've got more and more. Once again, that could be because the pressure, and also because of the marine life that lives down there, all the shells dropping down. That'll eventually make the carbonate fossils, sand and detritus, once again, contain carbon. But fossil fuels being burnt, you've got organisms doing this, like us, terrestrial deforestation, runoff of carbon dioxide and stuff like that, of different materials. All of it is going everywhere. So it's a constant cycle of carbon dioxide. So this is where it gets interesting. You've got carbon storage and oxygen short term versus long term. Short term, you have calcium carbonate, which are the shells of marine life that we talked about. You've got organic matter, which is dead plant life. You've got water diffusion, which is oceans, lakes, and whatever else you got there. But that's just the short term of where we see carbon existing at in our environment. Long term, you have calcium carbonate deposits, the limestone, the dolomite that I was mentioning before, fossil fuels, coal, and oil. As you look at these cliffs right here in the lower right, these are the White Dover Cliffs found in England. You might have seen them in some movies and stuff like that, but it's very interesting because what you're seeing there is basically chalk. You're thinking chalk? Yeah, like the chalk that you write on an old-time chalkboard. That's just chalk. It's marine sediments that have built up the shells over time. Now, you look at those, you're like, oh, how thick is that? Those are really thick. They're like 100 feet, if not more, cliffs. Massive. So when you think about how big a clamshell is or something like that, and if you had to stack so many of them 100 feet high, how many would there be? Then crush them all up into a powder, and how many would you have to get to make a column 100 feet high? Look at those cliffs. That is impressive. That is marine life that has died over millions of years. There must have been a lot of clams and other marine life that had shells to them to make cliffs that large. Now you might be thinking, how are they out of the water? Well, plate tectonics, upheaving of plates and stuff like that caused this to surface to the surface of the land, and now we can see them and study them, which is really interesting. But that was deep down in the ocean at one time, and now we can see it exposed. And that's what I find most impressive, is those cliffs right there and how many organisms there must have lived and died in those millions of years. So, nitrogen cycle, once again, we have lots of nitrogen. Our atmosphere is made up about 78% nitrogen. It's quite a bit. Process of converting nitrogen gas into usable forms nitrates. You've got nitrogen fixing bacteria. Take nitrogen from the air and convert it into usable forms. You have denitrification, converting fixed nitrogen compounds back into nitrogen gas. Okay, so what does that mean? Nitrogen fixation. And what we're doing is taking the nitrogen gas from the atmosphere and putting it into a nitrate. So basically, if you know anything about farming, nitrogen has the same charge as the soil, which means it does not like the soil. It's like two magnets, the same charge. They push each other away, they repel each other. So plants cannot take in nitrogen gas directly. They have to take it in through nitrates. This is why farmers in the springtime and the fall are always spraying their fields with nitrogen, because it bleeds out of the soil. And that's the only thing that plants can take in, some form of that. All right? So we're trying to find ways to do that to maximize production. Nitrogen fixing bacteria do exist in nature, and they form a symbiotic relationship with things like soybeans. And what they can do is they will bind with the roots, which I'm going to show you a picture in a minute, and they will actually form these nodules. They will harness the nitrogen from the atmosphere and then convert it into nitrates and give it to the plant, while the plant also supplies the bacteria a place to live and also food. So that sounds a lot like a symbiotic relationship that is mutualism, both benefiting equally. Okay, so denitrification is another important one here. I'll show you. There's the root nodules containing. Most farmers get really excited when they see those little things. A lot of people might think that'd be like cancer or tumors on the plant, but it's not. It's very, very good for the plants. So farmers get excited when they see these root nodules. That means they're going to have a good crop yield. All right, but denitrification is not as common. It's taking the nitrates and putting them back into the atmosphere. You're thinking, well, why do we need to do that? The nitrates can be bad for you. Have you ever heard of the blue baby syndrome? If you haven't, what happens is, if you think about it, if anybody has a newborn brother, sister, niece, nephew, something like that, you'll notice that many of the parents are buying distilled water. It's like they don't get water out of the tap for the newborns. And you're thinking, why is this? Why do they have to buy jugs of water that is distilled? It's because the distilled water has no nutrients in it, no minerals, no chemicals, nothing. It's just pure H2O essentially. And in rural communities, this is very big because farming, agriculture, all that nitrogen they've been spraying on the ground, once again, same charge, it'll be pushed out of the soil into the water system, which then goes into rivers, streams, and lakes in which we get our water from. So our public water distribution, they monitor this very closely and send out reports. But as an extra precaution, you want to be aware of this. So newborns, very small babies, small amount of blood, as they take in these nitrates, it actually binds to their hemoglobin, the red blood cells that transport oxygen to and from the body. And as such, they bind with it and won't let go. So they're basically suffocating themselves from the inside out. The poor babies do. They don't even know it because they're just trying to feed. So if you have distilled water, this doesn't happen. All right. So finding ways to get rid of this stuff is very important. Denitrification, a whole study was done by the Iowa State University, and they planned to eliminate nitrates leached into the water from farming. And what they did is they took a farmer field. They had to get this farmer to sign off on it. And he wanted to tile his field, and they said, that's fine. They said, instead of just tiling off into different directions, tile it into one location for us. And they dug this big trench, as you can see on the lower left, and they had a box there with a hose, which all the drain tiles came in there. And drain tiles, basically, they take the water off the field so it doesn't get saturated with water. And then they lined it with plastic, as you can see in the middle picture at the bottom, and they filled it with wood chips. Then they tarped it and covered it up with dirt and put these vents in there. And you're thinking, why in the world would they go through all this trouble? Turns out there is a bacteria that live in those wood chips that will actually do anaerobic respiration. Now, in doing so, they will, instead of doing a form of this, they will actually bind the nitrates and convert them into, get this, nitrogen gas. So they can actually take the nitrates out of the water, use it as kind of like an oxygen source, then convert it into a nitrogen gas, get rid of it out those vents as you see in the top right. So they tested the box on the lower left at the beginning where all the water came in for the levels of nitrates, and it was very high. And they tested on the other end, and it was very low. So a simple method, just using plastic, a ditch, and some wood chips, they solved a huge problem for this farmer and also the ecosystem. So easy ways to do it, very innovative, but yet very cool. Denitrification. And there's once again the nitrogen cycle. You can see there's some coming from the ocean, which diffuses in. There's a lot of denitrification from the ocean. Industrial fixation, which is us as farmers taking stuff out. There's entire factories do that. Biological fixation, like the soybeans and the bacteria. Denitrification, the loss of those things over time. That's just by weathering. All right. The phosphorus cycle. The cycle of phosphorus through the biosphere. This is an essential element for growth and development in organisms. And you think about it, it's vital for nutrient growth in plants. Plants have three main things. If you get to buy a bag of fertilizer, it has three things on it. It says N, P, and K. N for nitrogen, P for phosphorus, and K for potassium. So very, very important. You also have phosphorus. It's found in all your DNA, ATP. So it's a vital component for nucleotides. A very, very important nutrient for all of us that are living and have DNA. You've got the long-term and short-term cycle for phosphorus. Long-term, phosphorus is stored in rocks and is released through weathering process. So basically it's in the rocks, and the rain, the wind and stuff will strip away this stuff and it'll leach into the soil. Plants will uptake it, a primary consumer comes by, eats it. The primary consumer gets eaten by a secondary. All this phosphorus is being transferred from location to location to location, okay, through the food web. Short-term, phosphorus and phosphates is a solution cycle from the soil to producers and then from producers to producers. So that's your short-term. Now, phosphorus, as you look at this, all right, big web diagram here. But you can see the plants have it. They start off with a lot of it. Once again, you can see that there's loss to deep sediments, which cause the rocks to form over time. That's the precipitates as well. It's coming out of the water. But then plants get eaten by other things, decomposers, land animals like bears and us. And then they go and make animal waste. So your poop has a lot of phosphorus in it. All right, so a lot of phosphorus is pushed out that way. And that's why poop is such a great fertilizer, because it has phosphorus. All right, potash and stuff like that can also have phosphorus and potassium in it, and that's why potash is like when you burn coals and stuff like that. You sprinkle it on a garden or something, but you get plants uptaking it, animals, all sorts of things. So the phosphorus just continues to go around and around and around. All right. So as you can see here as well, you'll notice that you have your uplifting of rocks, which was maybe from precipitate down here from long ago. That's had some plate tectonics, shoved it up. You got some stuff chipping off, got the rain washing it. It goes into the soil, plants uptake it. A primary consumer, once again, picks it up. They have detritus, which is the dead things are going to move things around. Detritivores, once again, eat those dead things. Got decomposition, goes back into the soil, goes back to plants, comes again, once again from rocks and soil, goes back into the water. So it's an entire cycle. It's just everywhere, going around and around. So, summary, biogeochemical cycles include the exchange of important elements between abiotic and biotic parts of the ecosystem. The carbon-oxygen cycles are closely intertwined because, once again, photosynthesis, cellular respiration. Nitrogen gas is limited in its ability to enter the biotic portions of the environment, once again, because a lot of times plants need nitrates. They can't take in nitrogen gas. Phosphorus and carbon have short-term and long-term cycles, once again, a lot of times locked away in rocks or dead material. Okay? And sometimes we release them by weathering or by burning them directly as fossil fuels. Won't make you do the review today, but we'll go over this next time and talk about it. If you have any questions regarding the review, just send me an email. I won't be available. I won't see you Tuesday, Wednesday, Thursday, or Friday. So you'll probably have your test on Friday. So make sure you ask questions through the Google Classroom, email, whatever it may be. Okay? So you'll have some time to work on your study guides in the next couple days, but this is very, very important that you look it over. Okay? Have a great day.